Hi viewers, welcome to LMS Solution. Today we are going to see about MATLAB simulation of PID control tuning for buck converter. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. So today in this video we are going to see about designing of buck converter and then how that buck converter is implemented in the MATLAB, and then we go for a voltage control method in the buck converter, that means output voltage control method by using a PID controller, and then we go for a tuning of PID controller by using available method in the MATLAB. So these are the things we are going to see we are going to see in this video. So first I am going to start with designing of that buck converter, that means designing of L and C value for the particular rating, right? So I'm start with that process. So here you can see that, so these are the detail, that means design equation detail for that buck converter. So I'm going to design 250 watts buck converter. So here we need to provide the power rating of the buck converter, and then we have to provide the input voltage. So I'm going to fix the input voltage of the converter is 40, and output voltage I'm going to fix 20, and then switching frequency of the buck converter is 10 kilohertz. So next we have to calculate IOT max, so the maximum output current in the load side. So next we have to calculate a ripple inductor current. Next you have to calculate a ripple capacitor voltage. So this ripple inductor current is calculated based upon the load maximum current, so is multiplied with some percentage. So here I'm going to consider 0.01 times of IOT max, and then ripple capacitor voltage is calculated based upon output voltage is multiplied with some factor. So here I'm going to consider that factor is 0.01 percentage. So next, based upon this detail, you have to calculate L and C value. So this is formula for calculating L and C value for the buck converter. So next you have to calculate the load resistance value, so which is equal to output voltage divided by the maximum output current of the buck converter, and then you have to calculate duty cycle, so which is equal to V out divided by Vm. So these are the basic equation used for calculating that L and C value for the buck converter. So I'm going to execute this program. So after executing, so you will get value for L and C, and then load resistance and duty cycle. So by using this value, so you are going to construct that buck converter in the MATLAB. So for that, I'm going to click home and then click Simulink, and then I'm going to use a blank model. So first we need a DC voltage source for 40 volt, right? So I'm going to type DC voltage source. So the voltage is, I'm going to input voltage is 40 volt. So we need MOSFET, right? MOSFET switch. So I'm going to take MOSFET switch. I'm going to connect that MOSFET switch here, and then we need diode. I'm going to use diode, not this one. So just you have to take diode from this one. Okay, you got to use this one and connect like this. So next we need to connect the filter, inductor, and capacitance. So for that I'm going to use RLC series branch. RLC series branch, and I'm going to connect this one. So I'm going to take another one series RLC branch. I'm going to connect like this, and one more RLC branch. So this is going to act as a load. So here I'm going to change the value to L, right? Branch type is L, and then here branch type is C, capacitor, and then this is branch type is resistance. So here we have that value, right? Just you got to type that value 0.008, and then capacitance is 7.8125 e minus 6 e power minus 6, and then resistance is 1.6. Okay, so next we need to generate the pulse for the MOSFET. So based upon that output voltage, so as per our design, this output voltage requirement is 20 volt, right? So we need to measure that output voltage. So I'm going for voltage measurement. Take this voltage measurement and connect across that load. So and also I'm going to measure the current through that load resistance. So I'm going to connect here. So next I'm going to use go to block, connect this here, and then another go to used for connect this current measurement. So here I'm going to name it that when go to tag is V load. So this is going to be changed to I load. So next I'm going to take this V load. So this actual voltage should be compared with the reference voltage, right? So for that I'm going to take constant block to specify the reference voltage. So here our reference voltage requirement is 20. So next we need to compare this both reference and actual. So for that I'm going to use sum and then rotate. I'm going to connect reference and actual just to change the sign plus minus. So next it's going to be processed via PID controller. And then output of PID going to be processed via PWM generator. Okay. So it's going to be connected to MOSFET. Okay. So the PWM generator generate the pulse for that MOSFET. So based upon control signal from the PID controller. So next you have to measure the waveform. So by using scope, just you have to click this one, and I'm going to see the three things. So one is load voltage, load current, and the duty cycle variation. So this is duty cycle, duty, and then I'm going to measure load voltage. So this is load voltage, and then I'm going to measure load current, right? So here I'm going to measure load current. I'm going to fix the stop time is 0.5 seconds, and then you have to check the results. So here I didn't tune the PID parameter, so I taken the value as it is. So whatever value is fixed default, right? So I would take as it is, and then I'm going to check the response of the system. Now I think we are getting some error, right? We will get right. So because we are using power system block, right? So we need to use another block, nothing but power GUI. So now submit the model. So now it will be work. So now we can see that. So there's a variation of load voltage, load current, and then duty cycle. But here you can see the variation of load voltage. So our requirement is 20 volt, but it maintain around only 19.5 volt. Okay, that means the error, steady state error is around 0.5 volt. So we need to reduce that one. Okay, so for that we go for tuning method. So here our aim is minimizing the error. Okay, so I'm going to use PA controller, and then I'm going for tuning method. So this is tuning method already available in the MATLAB. So I'm going to use this tuning method. So I'm going to click tune. So click tune. After that, it will open another window. So in this window, you can go to plant, right? This one, plant, and then click identify new plant. So here we are going to identify the data, and we are going to identify the some data. So here I'm going to use simulate a data. That means here we need to tune PID or PA controller parameter. So the output of PID going to be considered as input for that plant. The input for the PID controller going to be considered as data, output data of the plant. Okay, so that means here, so this is input of the plant, so this is output of the plant. So here the input of the plant is nothing but duty cycle, the output of the plant nothing but error. Okay, so we are going to provide the duty cycle data. So based upon duty cycle data, you have to collect the error as the output data of the plant. So we are going to identify this plant by using this concept by supplying the duty cycle. Okay, so here you can see that the sample time is considered 0.005, and stop time is 0.5 seconds. Okay, that means already we fixed the stop time is 0.5, so the stop time is 0.5 seconds. Answer lag nothing but we are going to change the duty cycle from some object value to another value. So because we are going to use step response concept, this one. So initial offset, so here already is fixed to 0, right? So here I'm going to use offset value of the duty cycle is 0.2 initially. So now is 0.2, right? Here you can see that. So this is input signal for the plant, right? It's 0.2. So I'm going to fix amplitude. This amplitude I'm going to fix 0.4 second. This amplitude equal to 0.4 amplitude, right? 0.4 at 0.4 seconds. Okay, so here you can see that the amplitude initially from 0 to 0.25 is around 0.2. after 0.25 seconds, right, the amplitude changed to 0.6. So this data is given to that plant. So based upon this data, it will generate some error. So that error going to be collected from the plant. Okay, here I'm going to run the simulation. So you can see here the variation of load voltage, load current, and duty cycle based upon the change in duty cycle from 0.2 to 0.6 after a double run. So finally we see the identified data, identification data from the plant, right? So next I'm going to apply. So data is identified. So we need to tune that. That means we need to find out the transfer function for our system. That means our plant or our model, right? Based upon this identification data, so we need to identify the plant. So for that, for identify the plant, so here we have different kind of transfer function. So there are one pole, two real pole, and a damped pair, and a damped pair plus real pole. So many things is available. So I'm going to use underdamped pair transfer function concept. So after clicking that one, you can see here, right? So this underdamped pair transfer function. So these are the k, t, omega, and theta is the parameter of the transfer function. So that should be identified based upon this identification data. So for that, I'm going to go for auto estimate. So I'm going to estimate that parameter automatically. So after completion of this auto estimation, right? So you can see here, right? So the blue color is identify the plant, the green color nothing but our identification data. So both are match each other, and then here you can see that. So this is a transfer function parameter k, t, omega, and theta. Okay. So next I'm going to apply this plant. So I am satisfied with that plant parameter. So I'm going to apply this one. So next, after apply, you can see here, right? So the dotted line, nothing but actual plant response now, right? Actually, we are getting from the system. That means also I'm going to simulate this model. You can understand that one. So this is the plant response, right? Actual plant response. So after tuning, right? So this is solid line. So after tuning, it reaches to step input, right? That means error is minimized in the system, right? So for that, we need to fix the PID parameter, right? That means we need to update the parameter. So here you can see that. So after tuning, right, we get the parameter p equal to 0.05479 and ki nothing but 8.702. So this is the parameter after tuning, right? So here I already updated. So I'm going to click OK, and then I'm going to check the response now. Now we can see that the response goes to 20 volt, right? So it oscillate around only 0.1 volt, right? So it oscillate around 19.9 to 20.1. So the error almost reduced, right? Because without tuning, we are getting 0.5 volt steady state error. Now we are getting only 0.1 volt error. But if you take average, that the voltage, that means average voltage is around 20 volt only. Okay. So this is a tuning of this PID controller for DC-DC converter, buck converter. So next we need to check the model with the certain load change as well as input variation, right? So first I'm going for a input variation. So for that I'm going to delete this one, and I'm going to use controlled voltage source. So here I'm going to use control voltage source, and then I'm going to use star input repeating sequence star. So here I'm going to vary the input voltage in between 45 to 25 volt. So I'm going to take sample time is 0.1. So initial voltage is 45 and then 40 and then 35 and 30 and 25. Okay. So I'm going to vary this voltage like this. Okay. And then I'm going to check the response of the system. So now for example, we fix 40 volts, we are getting this one, right? So here 20 volt and then the current around 12.5. So the total power is around 250 watts, right? So now I'm going to vary this one and we are going to check the results, right? Now we can see that when the input voltage varying, right, from 45 to 25 volt. So what happened? The system still track the reference command. So it will be maintained at 20 volt, right? So, but during that variation of input voltage, it have some undershoot, right? And that means it goes to some low voltage around 19.5 volt and then come back to the 20 volt. So here you can see that it comes around 19.2 volt and come back to the 20 volt. So here it goes to 19, yeah, 19.2. So here it goes to 18.7 volt, right? So and then comes to after some seconds it comes to 20 volt. That means it track that reference command. So because of variation of this input voltage, so here you can see that the duty cycle variation. So it will be keep on increasing according with the input voltage level, right? Because the input voltage will be decrease from 45, 40, 35, 30 and then 25. So voltage is decreasing, so that's why the duty cycle is increasing nature in order to maintain a reference voltage at a constant level. That means it will be maintained around 20. Okay, so this is a variation of input voltage. So next we check with the variation of load, right? So here I'm going to fix the voltage is 14 and then I'm going to do some another arrangement now to vary the load resistance. So here I'm going to take the power is 50 percentage and then after some time I'm going to add, initially I'm going to consider 50 percentage of load. After some time I'm going to add another 50 percentage of load in the system. So here I'm going to use circuit breaker on this one. Skip and go to electrical specialist power system fundamental blocks elements. So here you can see the breaker, okay, this one. So you use this one now to vary the load. Just you have to connect this one here and then connect here. So I'm going to use internal timings. That means the load going to be connected at the time of 0.25 up to 1 second. Okay. So from 0 to 0.25 seconds, we are going to use 50 percentage load. So after 0.2 seconds, this load will be added in the system. That means the total load will be is equal to full load, right? So next you go to see the variation of load voltage, load current duty cycle. Okay. Now you can see that. So for the 50 percentage of load, the load current is around 6.5 or 6.3 amps. So you can see that the load voltage maintained at 20 volt. After changing load from 50 percentage full load, right? The voltage goes to some level and then come back to the 20 volt. and here you can see that the load current is maintained at 12.5 amps. Okay, so and also you can see here that because of change in load condition also, the duty cycle change from this point to and this point, right? Some variation is occur in the system. Okay, so this is a variation of load voltage, current, and duty cycle for a sudden load change. So even though for input variation and load variation, right, the controller effectively track the reference voltage command. So by using this, you can use this concept for tuning up PID controller for any converter in close to. Thank you for watching our videos. So kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much.